Everybody's quite right to be talking about the drought. We did have flow in the river this year, as you saw, and the peak flow at Barstow was 150 cubic feet per second. The peak flow at Victorville was 2,400 cubic feet per second. Most of that water goes in someplace underground between the Glenwood Fault up by Silverwood Lakes and Barstow, primarily in Hinckley. But you're quite right to be concerned about the drought. That's a drop in the bucket. During 1993, when the river flowed, the peak at Barstow was 15,000 cubic feet per second, so 100 times more. Within the period of record, the river has flowed at over 100,000 cubic feet per second. So this was just a small amount of recharge. The ponds at Glenwood, you're right, 4 acre feet a day is nothing. They will take 10 to 12 vertical feet of water per day. I think they're like 10 acre ponds or so. So you could get anywhere from 100 to 120 acre feet of water per day in there. This is a year to do it, because my understanding is the way DWR delivers water in wet years is you just pay for the cost of the electricity and move it south, and there's no cost of the water. So it's good that you've got Mojave Water Agency on board with you. So I've got about 12 slides. Not very much, but I can say a lot of words about an individual slide. The first 2 slides are sort of housekeeping slides about the status of the background study, and I'll explain to you where we're at and what we expect to be happening in the future with it, and when you can expect to start seeing something. Then just the review process and what happens once I say, yes, I have a draft, and I send it out to the community, I send it out to the various TWG members, and most importantly, I send it out to the USGS members elsewhere in the country for review, and why that takes a long time. And then I've got 10 slides, and they're mostly pictures. I hope you'll find them nice to look at and pleasing to look at. They're somewhat interesting, and hopefully, because they're pictures, that'll limit the brain damage, and I won't be saying too many big words about them. And then just finish up and wrap up. So let's see if I can make this work. Where do you push this? Okay, great. So this is a timeline for the background study, and we are out here in 2019. Officially, we are running behind schedule. We had hoped that we would have it on my clock. I was thinking March. Anne told me she was thinking February, but I have in my possession drafts of every chapter in the manuscript, with the exception of the review chapter of the PG&E model and the final conclusions. It's a big study. There's a lot of information in there, and it just takes a lot to put it together. I'd rather have it done completely and as correct as possible than have it done on time. Right now, task 8 is more or less complete. They have another set of experiments, another time step to run, and we'll run that after the report is in review to fill out the additional data points. We've had updates to the TWG. Yes.
Can you just explain to people what's task 8?
Oh, thank you. Yes, task 8 is the experimental work that is being done by my colleagues up in Menlo Park, and we're looking at 2 things there. We're looking at what happens with chromium in the in situ reduction zones within the aquifer, and these are batch experiments, and what we want to know is at the actual middle grain level, where does the chromium end up when it's reduced? Is it going to be refractory, which means non-reactive, and stay put, or is it likely to be mobilized in the future? And there are 2 experiments there. One looks at how tightly bound it gets with the mineral grains, and the other one looks at how rapidly it can potentially be remobilized if oxid conditions are restored to the aquifer. That's the one that has another 2-year time step to be completed. We've gone through and updated the technical working group with our results that we have so far. I owe Betsy another update on that information. I'll talk to her later about that. We'll probably schedule that for some time in May. The data are all collected and interpreted. I've gone through with the TWG the methods and preliminary numbers that we have for estimating background, and really it's a complex report. It's going to be many chapters. But the reality is, probably for Ann's board, what they're going to look at most closely are a table of 4 numbers and 1 map. And at that level, it's a very simple report, very easy to understand. If you need to know where those numbers came from, you want more information, that's what the report is for. It's the sort of thing you might want to read in reverse. Just take a look at that, and if that's what you need to know, very good. That's the sort of numbers that will be worked with by the regional board and with PG&E as we move forward in the future. So right now, we're kind of looking at the model becoming available sometime in early July, and I would like to hope that I can have a draft available towards the end of September, and we'll see if I can make that goal. This is the USGS review process, and the USGS has been around for about 150 years, and the process itself hasn't changed very much at all in that time, but it does get reviewed and updated. It was last reviewed by the National Academy of Sciences in 2017. I kind of participated in that review. And really what their comments had to do were how we manage review comments, how we store them for public access, and how we manage our data and make that publicly available to everybody. And already, in response to their comments, we put out 2 interim products, which are data releases, which are things that don't fit easily into our computer system, and they're online available. People can look at them. You have access to exactly the same data on the aquifer solids and mineralogy that I have. Everything that we have is available online. You have access, again, to the same water chemistry data that I have. You have access to the same geologic and geophysical information that I have. Those data are all there. Once I get to the point where I have a reviewable document, it'll go to my supervisor. She'll look at it, decide it's complete, hopefully, and it will move on from there to the technical working group and to the USGS colleague review. The colleague review is 2 independent reviewers someplace else in the country that will look at this. Because the report is so large, I doubt that I'll be able to find 2 individuals willing to look at the whole thing. So I'll probably farm it out to 5 or 6 or maybe more people within the survey who will look at bits and pieces in various chapters of it. The technical working group, maybe 4 elements within there. The Lahontan board will review it. You'll review it probably with an eye towards technical accuracy, but also with an eye towards how usable will this information be for your board for decision making. PG&E also will probably review it for technical accuracy. They have a high level of expertise out here, and they know the system probably better than almost anybody. So I look forward to strong technical comments from them. And they'll also be concerned about how usable it is, how clear it is for them to manage the system in the future. The IRP manager, this is the first I've heard that they'll be getting together with the community to discuss the content of the report and work people through it. That's a really good idea. I think everybody will benefit. And I really want to hear the comments from the people in the Hinckley community. And if nothing else, even if the comments are, I just don't understand this part of the report, I can work on that. It should be something that is at least understandable. And so that's what we're striving for. And then the technical working group members, which will be part of that group, people like Roger have participated in the process all along, and you may want to look at certain parts of it just independent of Riddell and that group, just because you have knowledge and have probably some interest in things that we've said along the way. Each one of these blue lines, unfortunately for me, represents the report being returned to me with comments. Review comments are, by their nature, never positive. I've never, in my 40 years of working for the USGS, had comments that say, great job, you don't need to do anything at all. There'll be a lot of work. They'll generally be negative, things that I need to fix. I'll consolidate those comments that come back from the TWG review and from the USGS colleague review. They go to my supervisors. Then they go to a team of specialists within our water science group, and it'll be reviewed by a groundwater specialist, someone who's very familiar and knowledgeable with hydraulics, groundwater geophysics, and geology. A water quality specialist, someone who's very, very good with water quality, chemical speciation, understanding geochemical processes. They'll be looking for it as a technical review also. And a data specialist who will actually look at our data, make sure it's where I say it is, it's accessible by the public, and can be readily retrieved if anybody wants to go through the same exercises that we did, they'll at least have access to the same basic data and go ahead and make the same basic calculations. After that, goes back to my supervisor again, who I'm sure will be immensely pleased to read it one more time. Then it goes to the Water Science Center review. I've tried to, as much as possible, work with those people along the way. They've seen preliminary chapters, they've given me advice about how to word things, how to handle things. So hopefully there will be no surprises. Hopefully I'm moving in line with what they expect, and it's all going to fit together nicely and flow smoothly. We'll do everything we can to expedite this process. It's my job not only to respond quickly to the comments, but to make sure it doesn't get stuck anywhere on anybody's desk. If somebody says they're going to review it, I have to hound them and make sure they review it in a timely fashion so I get those comments back. But not so much that I get poor comments back. I want them to do a good and thorough job. Then it goes to our editorial and technical standards review group. The official USGS technical standards group or book guidance document is the 1902 Chicago Style Manual. I expect that because this is a relatively high focus project that I'll actually get a technical review at that point also, and they will look very closely at this. At that point it goes to USGS Director's approval. At that point we have a report that's referenceable. It goes on to our publication unit for publication. We'll try to do this as a professional paper, which is a very high standard USGS publication. Up until that point of approval, anything I've told you and all the TWG working groups, anything that I've put out intermediate, anything that I say today is just a presentation. It's not a USGS report. It doesn't have director's approval and doesn't have that stamp of authority that one would expect from a USGS report. This process takes time, and there's a lot of work still ahead of me. You like to think you're done when you get the draft review out and you get those first set of comments back, but there's a lot to do. Any questions about how this moves forward and where we're at now on the report? Yes, Ian.
So in the left-hand column, in terms of kind of critical review, value added, I mean, where's the biggest chunk of that? Is it under the specialist review?
No, it'll actually be in the colleague review.
Okay.
Those could be highly technical. Those people are expected to do technical review. I also expect very technical comments from the regional board and from PG&E. And so I would not expect this project has been looked at thoroughly all along the data collection, development, and everything by the specialists. So I would not expect that they would look at something and say, your basic approach was wrong, but it's very possible that they might look at something and say, the way you made these series of calculations could be improved by using a different technique. That's not something I would want to hear at this point, because it could be potentially a lot of work to fix a comment like that. So we'll see. We'll see what happens. I would like to think that most of the comments will be things that are relatively easy to address. Any other questions?
Is there a statistician review in there?
There is not. You know, as far as that goes, the technical reviewers will look at it. If we get to this point here at the specialist review where they feel that some of the statistics I have in there are beyond the routine that they're normally looking at, which they are, in fact, there's plenty of expertise within the survey to send that out for additional review and comment. And so that can be done, you know, at either step. You know, some of the colleague reviewers may just come back to me and say, I don't feel I was the appropriate person to look at this chapter. But particularly if I farm it out to a number of different people, you know, those chapters that are heavy on statistics, they can go to somebody who's well versed with that. Usually, just a personal preference, I like to have someone who's very high level look at it, but also like to have someone who's relatively junior, so that from that standpoint I get the best possible opinion, but I also get, you know, is this going to be understandable to people? And so, you know, it's you want a mix of different levels when you review it. Also, if you know, that would be a fair comment for you or PG&E or somebody else to make if you're uncertain with something that's been done or the way it's been done, to just say, could you have somebody look at this specifically and see if there was another way or a clearer way to present this or to do these calculations, or can you just explain more what was done? Any other questions? Yes.
What's your best guess for how long that?
In the morning when I wake up and I'm all enthused, I say, oh yeah, we'll have this. That process will take a year or so. By the end of the day, when I realize how little I actually accomplished and how tired I feel, I despair of ever having completed it. But you have a report now at this point. There is a report there, and it's at a point where it will, even in my absence, it would be completable. So we're there. Any other questions? Yes, Betsy.
So the blue arrow shows the TWG comments going to the supervisor. Is that what was meant by that, or does it go up to the colleague review?
No, after, those will happen simultaneously. You'll get it at the same time as colleague review. And when you come back with your comments and the colleague review comments come back, I'll try to do those all at the same time. And in this case, I'll have perhaps as many as 6 sheets of paper. That's usually how I do it. I'll spread each review comment out per page or per figure, look at them all at once, make whatever changes I need to do, move on to the next one. And so, I've got a big table and just sort of spread out and work it that way. So I'll try and address your comments at the same time as everybody else. So that way I can look and see, my gosh, Betsy made exactly the same comments as the 2 survey colleague review comments. I better take that one really seriously. Or, quite frequently you get comments that are completely opposite of each other. And then you're like, well, I just have to make my best guess to point this out to my supervisor and hope that they decide that I made the right decision. At this point, the supervisory review is no longer a technical review, it's really a process review. And Claudia will go through it and she will make sure that I address the comments appropriately, that I responded thoughtfully to them, that if they require additional work or analysis, that I did that additional work and analysis. So that's not really a technical review from her at that point. Any other questions? Okay, great, thank you. Now we're into color pictures and stuff, and so it'll be a little bit more entertaining. You've seen this slide before, and this is a map of California, and there's Hinckley. The blue colors represent areas where regionally chromium concentrations are very low. The red colors represent areas where chromium concentrations are very high. Regionally, Hinckley is an area of very low chromium concentrations in the rock and alluvial soils within the boundary, within the valley. And that interpretation has not changed, and the numbers that we have as part of the background study reflect that. You'll see over here there are some chromium-containing rocks in the San Gabriel Mountains. I'll talk a little bit about those. But we're looking at very low numbers as part of the background study, comparatively. Certainly much lower than what you would see in the Central Valley up in that area near Redding. And that has not changed at all during the study. One of the things that I try to do when I write a report like this, although you're most interested in a table of 4 numbers and a map, that's not what I want to write about. I want to write about how the chromium got there, where it's coming from, what are the processes that cause it to weather from rocks and minerals. Once it weathers from a rock and mineral, how does it get into the groundwater, and at what concentrations? And I feel much more comfortable with data that I can explain from a process standpoint as to why it's there than just reporting to you numbers or statistics of numbers where there's no understanding of basic geologic, hydrologic, or geochemical processes. So hopefully I succeed, and hopefully you'll understand the processes in addition to understanding the numbers. Most of the slides that you'll see right now will be very visual. They're optical mineralogy slides, and I'll be comparing those with groundwater concentrations that we see next to those materials. So it should be relatively straightforward. This is chromium in Hinckley Valley. That little fragment of mineral that you see there is called actinolite. It's part of a lithic fragment, a metamorphic rock. You can see it's maybe 300 or 400 micrometers across. That's about the size, that's 100 micrometers there. The average human hair is about 50 micrometers, so please don't pluck the hair from the back of the person sitting in front of you, so, you know, for scale, but just take my word for it. It's relatively small. That's a sand grain. That comes out of Hinckley Valley. It comes out of a site that we call BG5, which is upgraded from the compressor station. It's a site that we would believe would be very natural. It's also a site that we call Older Mojave River Alluvium. Dave Miller, who's been the geologist on the project, who's worked with us, tells us that this material was deposited by the Mojave River about 300,000 years ago, and it was eroded from the Blue Ridge in the San Gabriel Mountains near Wrightwood. And I've climbed that ridge, and I've stood up there, and there's a 30-foot high wall up there of this stuff. And that's actinolite. It's a metamorphic rock. It's an amphibole. It has chromium concentrations that we have measured as part of the study that range from 900 to 4,000 or so milligrams per kilogram.
What's that parts per billion?
That is parts per million.
That is parts per million.
Same, it converts equivalently. Now that's not water, that's solid. Okay. There is a chromium mica up there that is even more concentrated, and the chromium in that chromium mica is actually in the percent range. So it would be about 10,000 parts per million or milligrams per kilogram. So there are some chromium, and I showed you on that regional map, up in the mountains. This material has eroded from those mountains, has been transported by the Mojave River. When you get those infrequent flow events, it's been carried 70 miles down the channel of the Mojave River. If you look at this, it's kind of rounded, looks a little beat up. That's from rolling around in the riverbed with the flows of the river as it gets carried down and ultimately gets buried in Hinckley Valley. This is a trace mineral. There's not a lot of it, but it is diagnostic of older Mojave River alluvium. You only see that this far out in the desert when you're in older Mojave River alluvium that was deposited anywhere from 1 million, 1.5 million to about 300,000 or so years ago. The total chromium burden, even though this stuff is really, really high in chromium, maybe as much as 4,000 parts per million or milligrams per kilogram, it's a trace mineral. It's present at less than 1%. You can find it. Krishangi hates me because I made her sit there at the microscope and look for this stuff. But the total chromium burden in this sample is pretty small, range from 10 to 23 parts per million or milligrams per kilogram. So not a lot of chromium there. The chromium, 6 concentrations in water that's in contact with this material range from about 1.4 to 2.2 micrograms per liter or parts per billion. So it's there, you can find it, you can measure it. The mineral itself has high chromium. When it averages out with all the other minerals that are in there and buried in the deposits, there's not a lot of it. It's measurable. You see it there. And it doesn't produce an extraordinarily high concentration in the water. This mineral's been beat up, weathered, it's fractured, dissolving to some degree. You can see some iron oxide on there. So it is reacting with the water. I'll talk more about the iron oxides in a minute, but that is diagnostic of older Mojave River deposits. This is Mojave River alluvium present day. If you go down to the Mojave River, this is what you're picking up. And if you looked at it under a microscope, you would not find actinolite in there, at least not very much. What you would find would be a mineral that's also present in the older Mojave River, but it's called magnetite. Chromium substitutes within magnetite. And so it occurs within there, sometimes at fairly high concentrations. This is actually a rock fragment, and so the magnetite hasn't eroded from it. Again, there's that 100 microgram per liter to human hairs. These are pretty small. They're very fine mineral crystals. They're very tiny, containing very, very high concentrations of chromium. That's half a human hair's thickness right there. This is X-ray dispersive spectroscopy. We hit that material with an X-ray. We elevate the atoms, the electrons in the electron shell around the chromium to a higher excited level, and when they fall back, they emit at various kilovolt ranges here that we measure their intensity. And so that's how we know how much iron we have and how much chromium we have in the sample. This one up here, at this point here, chromium is dominant. So it's not just a chromium containing magnetite, it's chromium rich magnetite. We did not find any chromite anywhere in any of the samples that we looked at in Hinckley or Water Valley. Chromite would be the most common chromium-bearing mineral that one would find anywhere else in the world. And chromite would be almost no iron, almost pure chromium, same mineral structure, looking very similar. The burden of chromium in recent Mojave River coarse sediments is fairly low, 10 to 12 milligrams per kilogram. It's higher in finer grain materials, but for coarse sands, which is what we're looking at here, a number like that. If you go down to the Mojave River right now today after yesterday's flow and look at this stuff, you'll probably get a number of about 5 parts per billion. So it's actually lower with time with some of this older stuff. It's present in very, very low abundances. What we have to do to find this is we take the sample, it takes about 5 pounds of it, and we put it in a dense mineral, a dense liquid. Methylene iodide is what we use now that has a density of about 3.5. All the light stuff floats, this stuff sinks, and then we analyze for this material, which has a density of about 5.2, specific gravity about 5.2, to be a density of 5.2 grams per gram. And it's low abundance, it's very resistant to weathering. Because actinolite is not present, the magnetite that's present in recent Mojave River deposits is low abundance. You have low chromium burden. Because it's resistant to weathering, the chromium in the water in contact with these materials tends to be very low. And a typical number for that might be less than about 1.5 parts per billion. You do have some local sources of chromium here. And this is Iron Mountain, which is, I guess, that away. Hornblende is a mineral that we find up there, and it's in a rock called hornblende diorite. This is a picture of an outcrop in there looking across the western part of the valley. Looks like that. If you whack it with a rock hammer, it looks vaguely green. If you drill into it, particularly in the western sub-area, it looks like this, kind of green. Here's the minerals here. Take a look at that mineral. Here, this is kind of right down there in that area there. You notice it's not rounded, it's angular, it's fragmented, it's fresh from the rock. That's pretty recent. In that sample, the hornblende was a major to a minor mineral, major being 5% or more, minor being 5 to about 1%, trace being less than 1%. And the chromium burden and that material coming fresh off the mountain in that sample is somewhere between 190 and 210 parts per million. So fairly high. The average continental abundance is about 185 parts per million. So you're getting up into the average continental abundance there. So it's not high on the global scale of things, it's certainly high for Hinckley Valley. As it gets down into the alluvium in the valley where you draw water from, it's physically diluted by mixing with solids from other sources. And now it's a trace mineral. We don't see very much of it. We have to look hard for it. The chromium burden in this sample, this is down gradient from the western excavation site, was about 9 to 16 milligrams per kilogram, a little bit higher than Mojave River sort of materials, but not particularly high. Interestingly enough, chrome 6 in contrast with that was about 6 to 6.5 micrograms per liter. Let me say something about that. You look over here, here's material that we drilled into. This is actually pure hornblende diorite, 165. Concentration, chromium burden on there was about 300 to 600 parts per million, about twice to 3 or 4 times the average continental abundance. Pretty high. Chromium concentrate, water in contact with that, about 1 to 1.2 micrograms per liter. We didn't sample that well because we knew it didn't have a lot of chromium. We did sample 153, which had pretty high chromium concentrations, about 3.3 parts per billion. The material looked very similar to that, about 61 to about 250 milligrams per liter, about the average continental abundance. So geology doesn't explain everything. Downgraded from the Western Excavation Site, we looked at this really hard, really closely. The hornblende there is not capable of producing these sort of numbers. This is a typical number that you get from geologic materials in Hinckley Valley that are among the higher materials in Hinckley Valley. So about 3.3, maybe 3.9, somewhere in that type of range there.
So, John?
Yes.
When you use the words water in contact with that, which you've used a few times in these slides, what's the process by which you get the solid sample, you analyze it, and then you get the water in contact with that?
What we've actually got here is there is a tremendous archive of core material that PG&E has saved from all their work. So when I'm saying water in contact with that, what I mean is I know the screened interval of the well. I went to the core library and we analyzed all the material adjacent to that screened interval of that well. And so that's what these solid numbers are coming from. And so the water out of the well has last contacted that material. We didn't do an experiment, a leaching experiment or anything like that. So it was a good question. Any other questions? Okay. This material is from Water Valley, north of Red Hill. This material is from well 203D that underlies the western sub-area. Both of these materials are very old geologically, or older than Mojave River alluvium and even older Mojave River alluvium. They're from what is known as the Miocene age, which is 5 to 20 million years ago. So this stuff has been buried in Hinckley Valley, sitting there reacting with water for 5 to 20 million years, much different than the materials that I just showed you previously in the alluvium that has maybe reacted and sat in the groundwater system for 300,000 years. In the course of 5 to 20 million years, you can see these mineral grains and you see they're weathered. These are weathering lines on those mineral grains up in Water Valley. Down here, when we look at 203D, we see etching, we see pitting of the minerals. And in both samples, we see a high amount of iron oxide materials on the surface coatings of those mineral grains. These mineral grains are not particularly high in chromium. When you look at the burden here, the solid in Water Valley, 6.7 to 22 milligrams per kilogram. In 203D, 20 to 44 milligrams per kilogram. But they have sat there for 20 million years, and those mineral grains have disintegrated. Chromium that's part of those mineral grains has come loose and is sorbed to the oxide coatings on those mineral grains. When we analyze those oxide coatings, what we find is that somewhere between 25 and 30% of the chromium in that sample is on the coatings, and it's potentially highly molded in the groundwater. The groundwater in these settings tends to be old. 203D is very old. It's the oldest water that we sampled in the area. Recharged or isolated from the atmosphere somewhere between 10 and 20,000 years ago. It's strongly alkaline. It has a high pH, as is the water in Water Valley. Under conditions of high pH, chromium readily desorbs from these oxide coatings and moves into the water column. So in these areas, you have higher concentrations of chromium. In Water Valley, water in contact with the screen, I guess is a way to say it, of this well, actually has a chromium concentration range from about 4 to 4.3 parts per billion. So compared to other things in the valley, that's starting to get up there. 203D, water is very, very old there, has chromium concentrations that we sampled ranging from about 5.5 to 8.9 parts per billion. This well at one time produced water having a chromium concentration approaching 20 micrograms per liter, which would be above what was the MCL for chromium in California that was rescinded in 2014, I believe. So you have the potential, given mineral weathering sorption and then desorption of very, very high chromium concentrations within groundwater in certain areas within Hinckley Valley and Waterville. This is what appears to be a very complex diagram. Shows pH on one axis, EH on the other axis, which you could think of maybe as oxidation potential. Highly oxic here, oxygen present. Reduced here, oxygen not present. And what we're looking at is all the samples that we collected as part of the background study posted on there. And they're very tightly grouped. We calculated EH from our Chrome 3, Chrome 6 couple. We have very good, very well-behaved data. And we can make some interpretations from that data. But when we look at it and we superimpose upon it the behavior of chromium and the behavior of manganese, we begin to understand a few things. Manganese is important because it drives the oxidation of Chrome 3 to Chrome 6. In the natural environment, that's how you get Chrome 6. What's in the rock, what we've looked at previously in all those rocks, is in the form of Chrome 3. It will be relatively insoluble in groundwater. It gets sorbed on those iron oxides that we talked about. If there's manganese present, and particularly manganese 3, it can be oxidized to Chrome 6. And here's what we're looking at right there. And that's an optical image of a quartz grain. That little black speck that you see there was analyzed using a Raman spectrograph, which actually looks at the vibrational modes of the electrons on there. And we know it's a cordonite group mineral. It's actually, I think, hollandite. It's a manganese 3, manganese 4 oxide. It's quite capable of taking Chrome 3 and oxidizing it up to Chrome 6. We looked at a lot of it. This is the primary form of manganese that we see in the basin when we look at it. It's present almost on every sample that we look at. This sample again is from BG5. Chromium ranges 2 to 23. Chromium in contact with that water, 1.4 to about 2.2 micrograms per liter. Visibly, these things can accumulate to the point where you can actually see them. They can be significant to look at. They affect the flow of the water. They affect the chemistry of the water. You start to see things like this up against the well screen, and we sample that water, and we get much higher concentrations of chromium because the chromium accumulates on these solids, on these oxides. There's manganese there, and so not only does it accumulate, but it can be oxidized to Chrome 6. Once it's oxidized to Chrome 6, if you have alkaline conditions in the water, it comes into solution. Chromium concentrations in a well in contact with this material here were about 3.9 micrograms per liter. So we're looking at some significant concentrations here relative to the 3.1 background concentration. And you can look and see this type of material at geologic contacts throughout the valley and at lithologic contacts throughout the valley. Look at this diagram very closely and you see there are some differences. Some wells that stand out when you look at them closely. I actually tend to believe these numbers. In particular, we'll talk about 133 and 154. They're in what is called the northern sub-area up towards Red Hill. They're just south of Red Hill. They're completed in fine-grained mudflat deposits or lake deposits, depending on how Dave Miller was feeling when he called them that day. When you look at the stuff, the best scientific word for that is smush, and it's just dark brown sort of material. In some cases, the core of this stuff is actually not oxygen anymore. It's reduced and it's blue-green. But it has dark structures within it, and you probably can't see it from back there, but there are round features that are dark brown in there. Those are manganese nodules. You may have heard that phrase relative to a number of other things related to oceans, related to things in the environment. And there are dendritic structures in there, look like tree branches. Those are called dragon's breath, if you're an old miner up in Colorado. And those are manganese structures that form within these complex materials. This is clay. This is true clay minerals. We've had it analyzed and looked at. And it also is of Miocene origin. The chrome burden from that is actually quite high. 82 to 94 parts per billion. It's not quite approaching the average continental abundance, but for Hinckley Valley, that's a high number. And we go through in the report how we decide what is a high number. These manganese nodules, we took those materials up to Stanford. We put them on an atom smasher I was talking about, and the Zane's a synchrotron light source. And we find out they're not manganese 3,4 minerals, but they're manganese 4. They're strongly oxic. And so they have the capability in their surface chemistry to take this high concentration of chrome and oxidize it readily, or more readily at least, to chrome 6. The chrome 6 concentrations in water from that well that's in contact with these materials ranged from about 9.8 to 11 micrograms per liter in our sampling. Historically, in PG&E's data, this well has yielded chrome 6 concentrations upward of 20 micrograms per liter. We did try to squeeze some pore water out of there. We got very low concentrations of chromium within the pore water. I mentioned get away from the surfaces of this stuff, and there's some reduction that goes on because they have a high burden of organic material also. But the water is extraordinarily alkaline with a pH of 9.4, very low specific conductance, very unique setting with a combination of Miocene-age materials that have eroded and weathered to the point where they form clay minerals. Manganese has accumulated in there to make these oxides that happen to be a particular form and can produce chromium concentrations that in this case actually approach and exceed the former California maximum contaminant level for chromium in drinking water. These wells up in this area are very poor yielders. They don't make a lot of water, as you might imagine, if they're completed in clay. The other ones that stand out are MW192 S and D, and those are in a similar environment, at least physically similar. They're near the playas in the eastern part of the sub-area, and when you look at them, they sort of look like they would be similar materials. When you analyze them, they're not. The materials in the northern sub-area are true clays. The materials in the eastern sub-area that comprise of brown clay are actually just Mojave River sands and felsic materials that have been ground and pulverized to the point that they're clay-sized texture. And so they're very fine, they're very small. You pick them up, they feel like clay, but mineralogically, they're not. And mineralogically, when we look at them on our electron microscope, when we hunt through them, we find a lot of quartz, we find a lot of feldspar, we find a lot of mica and things that come from the San Bernardino and San Gabriel Mountains. And we also find magnetite, which contains chromium. The burden of chromium on some of these minerals, about 16 to 30 parts per million or milligrams per kilogram, largely because of the fine-grained nature of the materials, not because of their mineralogy or their geochemical properties. Most of the chromium that we see in there seems to be again within magnetite. Water from wells in that area can be fairly high, 3.5 to 3.9, but when we look at the water from the wells, it's not the water that we see in the clays. It's affected by irrigation return. It's circumneutral. It does not look like that water. So, we have some questions about this area. The pore waters that we get out of there can be as high as about 3.3 micrograms per liter, chrome 6. Within the pore fluids that we squeeze, again, that water is pretty alkaline. pH is close to 8, very low specific conductance. The waters that we see in the well, in addition to having actually slightly acidic pHs, have very, very high specific conductances, and actually don't seem to be well related to the pore fluids. Again, there are manganese nodules that you can find in there when you look at these materials. So what I've done is I've walked you through a variety of geologic materials, and I've laid out some numbers for you to think about. In general, in many of these areas, the numbers are fairly low, but in some cases, they can get higher than the current 3.1 background level. When we identify those and we talk about those as naturally occurring chromium, which we will, I want you to understand why, how those evolved, where those materials came from. And that's what the report will explain, so that if you want to delve deeper into just a table of numbers that you need to work with for regulatory or engineering purposes, but you want to understand why those numbers are there, so that if I go to the next site I can think smartly about that. Or if I go to the next valley over, I can think smartly about that. Or if I go someplace else, anywhere, this type of information transfers in that way. And it isn't just Hinckley-centric. I would like to think that everything in this report and everything that I've ever told you is traceable to a number, a measurement, in this case, pretty pictures, but there's nothing here that we're going to provide to you that is not traceable to measurements that we've made as part of the study. So yes, Hannah.
Dr. Izbicki, you said that all this data is available to anyone who wants to look at it.
Yes.
Is there a URL or something that we can post?
You know, I was going to prepare that, and I had it ready to go. There's like 2 science releases already. There are, you know, the midterm report and the other report. There are links available to our National Water Information System that has the chemical data on it. And there are links that I can get you to the well logging files. And I'll provide those to Riddell so
And we
that...
can put them in
Yeah,
the
we can put them in the
newsletter.
newsletter if
Yeah.
people want.
Yeah.
Great.
Yeah, so that stuff is all available. In many cases, I will admit that it's finding your way around some of those systems
We
can
got
be kind of
Roger.
tough. Yeah.
Roger can do it.
So, any other questions? Well, I hope I get this many review comments too. This will be great. We'll have the report out in 3 months that way. Thank you all.
Dr. Izbicki, let's give him a big round of applause. You will be here after the meeting to answer